Okay, section 8.2 talks about proportions. Real easy stuff, okay? Think of proportions as fractions because generally speaking, that's how we're going to write them, as a fraction. And we all know about fractions, right? We all know we can reduce fractions. We can take, 2/4 and we can say that's equivalent to 1/2, right? Well, a proportion is something very similar, except we're missing a piece. For example, 2/4 equals some mystery x over 2. Okay, I need to figure out the mystery x, okay? And the way we're going to do this, it's kind of a neat technique, and if you think about it, we're clearing out the denominators. If I kind of did it the long way, and let me kind of do it the long way. Remember, this is a fractional equation, right? And we talked about equations, and we said, well, how do you get rid of the denominator? You figure out your common denominator, and you multiply through the entire problem by that common denominator, right? So in this case, it would be a 4. So we multiply numerator only by that 4. So here I get, what, 8/4 equals 4x over 2, which immediately looks worse, but then all these fractions go away, we realize. Aha! 2 equals 2x. Now it's an easy problem to solve. Divide by 2, and we get 1 equals x, or x equals 1. Okay? We knew it was a 1, because 2/4 is equal to 1/2. Okay? There's a slicker, kind of more direct way to do what we just did. We're just not kind of explicitly showing it, and that's called cross multiply. Okay? Cross multiply. Take these two and multiply them together, and take those two and multiply them together. Okay? It doesn't matter which I put on the left and which I put on the right. So 2 times 2 equals 4 times x. 4 equals 4x. Looks familiar, right? X equals 1. Okay? It's equivalent to what we did here. We didn't have a 4 equals 4x over here. We had a 2 equals 2x, but it's okay. It's an equivalent equation. Okay? We got the same answer. And that's the key. Alright? So proportions, we're going to do that. Just think of it as you're reducing or you're unreducing a fraction. Okay? We're not limited to nice integers, though. That 2/4, if I wanted to multiply by 3/3, I can get a 6/12, right? That's the same thing as 2/4, which is the same thing as 1/2, right? We're used to seeing nice, pretty integers, but we're not limited to integers, okay? And we'll see you don't always have to have nice, pretty whole numbers here. When we were reducing and unreducing fractions, we did. It would be silly, it wouldn't be wrong, but it'd be silly if we said, hey, let's multiply by 4.7 on the top and the bottom of this fraction, right? We could do that. We're going to get something. I don't know what it is. Let me pull out a calculator just because I said it, and now I got to do it. 2 times 4.7 equals 9.4. Divided by 4 times 4.7, 18.8, okay? It's weird, but there's nothing wrong. This is equivalent to that 2/4 we talked about, which of course is 1/2. And now if you stop and think about it for a second, oh yeah, half of 18.8 would be 9.4. Yeah, it's half. It makes sense, okay? Proportions don't limit us to the nice, pretty integers. We can have anything we want there, and we will have some cases where we trick it up a little bit. Okay, if we look at example 1 on page 387, okay, there's a few different parts here. Part A says x/4. The x can appear anywhere. Okay, it doesn't always have to go in the same spot. We've got two fractions. They are equivalent fractions. Why are they equivalent? Because there's an equal sign in between them. They're equivalent. One is a reduced or unreduced or simply changed form of the other. Okay? How do we find the missing piece? Cross multiply. Okay? 6x equals 9 times 4 is 36. Then it's easy, I hope, to solve. X equals 6. Okay, so we are claiming that, if you want to kind of restate the bold statement here, we are claiming that 6 over 4 is the same thing as 9 over 6. If we turned them into a decimal, we would, of course, really convince ourselves. But yes, that's correct. Okay? How about this one, part B? Now this tricks it up just to here. Instead of just calling it x, in this case I got 4x over 5 equals 17 over 20, over 20. Okay? They're two fractions, except that numerator really looks weird. It's a 4x instead of just a good old number. Well, oh well, that's the way it is. We're being asked to figure out what x is. Let's figure it out. Cross multiply. So 4x times 20, that's going to be 80x, right? So 80x equals 17 times 5. I got to think a minute and figure out what that is. That's 85. 80x equals 85. How do I solve that problem? I divide by 80. Okay, so x is not going to be a nice pretty number. It's going to be 85 eightieths. Can I reduce an 85 eightieths? Well, if I divide by 5 here, top and bottom, it does reduce. It reduces into 17 sixteenths. Now, some of you have that kind of reducing by division, like I drew the little divide there, and that's fine. You recall what I always do, though. I like to show all those factors. I like to say, aha, 85 is really 17 times 5. 80 is really 16 times 5, and then we cancel those 5s out of there. Okay, we could turn it into a mixed number, but no need, as long as it's reduced. I'm good with that. Alright, so that's it. That's the trick. There's not a whole lot to proportions. It's equivalent fractions is all it is, but I've got some missing pieces here. Okay, now look at this one. Part C tricks it up even more. Alright, cross multiply. Now let's be careful. It's x plus 8, every bit of that x plus 8 times 3. So again, and it doesn't matter which way I go. Maybe I'm not being consistent here, and I apologize for that, but it doesn't matter. As long as you cross multiply and put all the stuff on one side and the other stuff on the other side. So I had to write it like that. That entire x plus 8 is going to get multiplied by 3, so it's going to be a distributive process. Same thing with the other side. 5 is going to be multiplied by this entire parentheses. It's another distributive process, okay? Hopefully this part's a no-brainer now. 3x plus 24 equals 5x minus 10. Put your x's on one side, your constants on the other. Makes no difference. Generally speaking, I'll put the x's on the left unless there's an obvious reason not to do that. So I'm going to have negative 2x plus 24 equals negative 10. Here's where order of operations and just good old dealing with negative numbers can really haunt you. Okay, you should not have to think at all what is negative 10 minus 24. You shouldn't have to stop and think about it. Okay, hopefully it's an absolute no-brainer. You say, oh yeah, negative 34. Got it. You shouldn't have to think at all what this negative divided by negative is, right? It's a positive. And this will be a 17. Okay? All good there? Sweet! Okay, I'm still on example 1, part D now. Now this one's a little different here. Wait a minute. I thought you said proportion was equivalent fractions. I don't see a fraction over there. I see a 7. That's not a fraction, is it? Well, come on now. You know the drill. You know that math is fun, and you certainly know that fractions rule. Because I can take any good old whole number and turn it into a fraction. There it is. Now it fits the template. Some fraction is equal to some other fraction. I'm finding an equivalent fraction. It's going to be a weird number because there's no easy way to reduce the fraction of 7 over 1 and turn it into 3 over something, right? You know it's going to be a little weird, but that's okay. Cross multiply. 7x equals 3. Divide by 7, I'm going to get x equals 3 sevenths. Alright, it is just that easy. Almost too easy, I dare say. Okay, so this whole idea of cross multiply. Works for us here. Okay, I didn't say it generically before, but I'll do it now, and that of course makes it look harder. If there's some fraction A over B and it's equal to C over D, I can do the product of A times D, and that's going to be equal to the product of B times C. Okay? I can do it. Alright? Let's do it. Let's do an application, a little bit of an application. Not really, we just have some units thrown in here. Example 2 on the next page. Says solve for x to the nearest tenth, so we were told to round to the nearest tenth, so there'll be some rounding. We have 450 square feet per 1.2 gallons equals 1,250 square feet per x gallons. Okay, now, what is this? I don't know. Maybe gallons of paint. It didn't really tell us what the application was, but that would kind of make sense to me. 1.2 gallons of paint can cover 450 square feet. Okay, great. That's what it says on the label, right? Well, my walls that I'm trying to paint here, my house, whatever it is, it's 1,250 square feet. So how many gallons do I need? Okay. Let's find out. Cross multiply. I'll, generally speaking, again, keep my x's on the left, so I'll do this part of the multiplication first, and I'm going to drop the units because the units make sense. Square feet per gallon, square feet, x is going to be in gallons, okay? So 450x equals, I'm going to have to take 1.2 times 1250. So 450x equals, when I do that, oh, come on, book. The book doesn't tell me. Alright, so let's do it ourselves here. I got a different calculator here. My apologies, but I was playing around with a different one. What does that say? 1,500. Okay. Divided by 450. X equals 1,500 divided by 450. And we get 3.333 repeating, right? 3.333 goes on forever, and we were given some instructions to round to the nearest tenth, so that's right there. Round to the nearest tenth, 3.3 gallons. Okay? Now, introduce some practical, physicality to the problem here. If this was really paint, and we are buying paint to paint this wall, we're not going to round it to the nearest tenth of a gallon, right? We're going to round it to the nearest gallon, and we're always going to round up, right? The rules of math say we got to round down here. It should be 3 gallons. But if we're trying to cover this wall, we need more than 3. So 3 doesn't cut it. So again, in the real world, we're going to call that 4 gallons. Okay, but in the world of math, we were told to round it there, so we're going to round it there. Okay? All right, that really is all there is to this section. It's a short one, okay? So we're going to move on and talk about variation here in the next video. I'm debating whether or not to dive into it, but what the heck, we'll make it another video. So this is proportions. Let me just grab one more out of the book here. We'll juice it up with one more example. Oh, what looks good? Yeah, let's throw one with some decimals in there. This happens to be number 22 from this section of the book, but it doesn't matter what it is. 0.7x over 2.3 equals 5.6 over 12.8, okay? Equivalent fractions. They're just weirdo looking fractions with decimals. We're not used to seeing that, but whoop-de-doo, nothing we can't handle. If I cross multiply, I've got 0.7x, but then I'm going to be multiplying that by 12.8 equals 2.3 times 5.6. Again, calculators are best friend here with this one for sure. 0.7 times 12.8. 8.96, so I'm going to have 8.96x equals 2.3 times 5.6, 12.88, divide by that coefficient in front of x, so I'm going to take that 12.88 and divide by 8.96, and There were no rounding instructions here, 1.4375. No rounding instructions. Let's see, round to 4 significant digits as if necessary. There were rounding instructions. All right, significant digits. Remember how these are? Well, everything's a non-zero here, so it should be really easy. 1, 2, 3. That would be my 4th significant digit there, the 7. So I'm going to look beyond the 7, and it's, of course, 5 or more, so I'm going to make that an 8. 1.438. Okay, all right, we'll call it quits there on proportions. We're going to look at something called direct variation here next, which you'll see is very similar, very, very easy.